Imagine you could make a metal stronger by making it weaker. It sounds absurd, right? But that's exactly how we unlock the full potential of titanium. Titanium already has a reputation for toughness. Even its name comes from the titans of Greek myth. This metal is strong as steel while being 45% lighter, and it laughs in the face of rust and corrosion. Yet, to make titanium truly indestructible for the most extreme applications, engineers have learned a counterintuitive trick. They deliberately weaken it first. Today we will discuss this and much more about titanium. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic table and also do experiments. And if you like these videos and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, if you want to influence next week's element, make sure to fill in the poll in the community tab. So as we journey further into the periodic table, we stumble upon this gray metal. Now, if it hadn't been labeled, I bet many of you probably would not have guessed what it was. In fact, I would not have known it either, but it is titanium. Yes, the element known for its strength. As you can see, it's dark gray and not very shiny. Now, we do have something else here that I, Jeroen, the narrator, have once been given as a token of appreciation, and it is also made of titanium. It is a spinner that is made from pure titanium, and in this case it seemed to be more fun watching than just a raw element in the cube. Now, if I did not ruin the cube for you yet, and you still want to collect the periodic table or have a piece of titanium in a cube, make sure to click on the link in the description, use the promo code so you will get a 10% discount and you will also be helping out our channel. Now, titanium's story begins in the late 18th century. In 1791, an amateur geologist and clergyman named William Gregor, showing here the latest fashion, discovered a mysterious new material in the dark sands of a stream in Cornwall, England. Gregor noticed that these black sand grains were attracted by a magnet. Curious, he analyzed the sand and found it contained two oxides, one of iron, which explained the magnetism, and another unknown white metallic oxide. This second substance contained a metal that didn't match anything scientists had identified before. Gregor published his findings and named the new oxide Menachenite, after Menachem, the parish in Cornwall, where he found it. Little did he know, he stumbled upon titanium, though it didn't have that name yet. A few years later, in 1795, across Europe in Germany, chemist Martin Heinrich Klaproth independently rediscovered this new element. Klaproth was examining an ore known as rutil from Hungary when he realized it contained an unknown element as well. Learning of Gregor's earlier report, Klaproth confirmed they were the same substance. Klaproth is the one who bestowed the metal with its enduring name, titanium, after the titans of Greek mythology. More on that later. That wasn't an accidental choice. It reflected the strength and the power associated with this new metal. Throughout the 1800s, titanium intrigued chemists, but it remained laboratory bound. Why? Because extracting pure titanium metal turned out to be very difficult. Early on, scientists could isolate small, impure bits, but producing usable metallic titanium was a huge challenge. Traditional metal extraction methods, like using charcoal to reduce ore, which works for iron, failed for titanium. Now, if you try to extract titanium from its ore using carbon, like you would melt iron, the titanium grabs the carbon and forms a hard, brittle compound, titanium carbide, instead of pure metal. This affinity for carbon and oxygen made titanium extraction tricky. In 1887, chemists Nilsson and Pettersson managed to produce about 95% pure titanium by a chemical route, involving chlorine gas and sodium reduction. The first nearly pure titanium, 99% purity, was produced in 1910 by metallurgist Matthew A. Hunter. He invented the Hunter process, heating titanium tetrachloride with sodium metal at red-hot temperatures to finally yield titanium metal. It was a breakthrough, but still not efficient for large-scale production. The real game changer was developed by William Justin Kroll. In 1932, Kroll found a better way by using calcium to reduce titanium tetrachloride, and by 1940 he had refined it using magnesium instead. This became the famous Kroll process, which is still the primary method used to produce titanium today. on an industrial scale. At last, titanium could be made in quantities large enough for practical use. Once methods to produce titanium in bulk were established, the mid-20th century saw titanium transition from laboratory curiosity to a strategic industrial metal. During the 1950s and the 1960s, titanium emerged as a critical material in military and aerospace applications. The United States and the Soviet Union both recognized its potential. The USSR was actually an early adopter. They pioneered titanium for advanced submarine hulls, such as the Alpha-class subs. Because titanium's strength, lightweight, and corrosion resistance let submarines dive deeper and move faster. Titanium was so vital during the Cold War that it was deemed a strategic material. The US government stockpiled titanium sponge, the raw porous form of the metal, in case supplies were disrupted. An almost ironic Cold War tale is that the US secretly sourced titanium from the Soviet Union, the very adversary they were racing against. Now, in the 1960s, the CIA set up dummy companies to buy Soviet titanium ore covertly. Because the USSR had some of the richest titanium resources, this titanium was used to build the SR-71 Blackbird spy plane that would later be flying reconnaissance missions over the Soviet Union. Such stories underscore how rare and crucial titanium was at the time, and also how ridiculous the Cold War was. From the 1970s onward, titanium production expanded globally, prices gradually fell, and the metal entered more common uses. By the 21st century, titanium found its way into everything from commercial airliners to biomedical implants to consumer electronics. Now, how did titanium get such an epic name? Well, for that we have to thank Martin Klaproth and his flair for the dramatic. Klaproth chose to name the new element titanium after the titans of Greek mythology. Now, interestingly, William Gregor's original name, menakenite, didn't stick, probably because it referred to the oxide mineral and was a bit parochial. Klaproth's catchy mythological naming won out, and titanium entered the periodic table and popular imagination. Titanium's chemical symbol is Ti, and it carries atomic number 22. But in a way, every time we talk about titanium, we echo ancient mythology. This fusion of science and myth, naming and cutting-edge material after ancient giants adds a romantic twist to titanium's identity. It's not every day that an element's name conjures up images of indestructible giants hurling rocks in a godly battle. In titanium's case, the name sets the stage for a metal that indeed lives up to its legendary toughness. Now, what makes titanium stand out physically among metals? Let's explore its key physical properties in simple terms. Titanium is famously strong and lightweight. By strength, we mean the tensile strength. How much pulling force can it handle without breaking? Pure titanium metal has about the same strength as some common grades of steel, yet it is almost 45% lighter by weight. To put this in perspective, if you had two bars of the same size, one steel and one of titanium, the titanium bar would weigh nearly half as much as the steel bar, but could bear a similar load. Titanium's density, about 4.5 grams per cubic centimeter, roughly midway between aluminum, lighter, and steel, heavier. It's denser than aluminum, which is why titanium items are not quite as feather-light as aluminum ones, but much less dense than steel. This means titanium strikes a sweet spot, not too heavy, not too soft. Now, in practical terms, a solid titanium object is 60% heavier than the same size aluminum object, but will also be much stronger. It's this balance that makes titanium ideal for applications where both strength and low weight are critical. Titanium is a hard metal, though not the absolute hardest. Some heat-treated steels or specialized alloys can be harder, meaning more resistant to scratching or denting than titanium. However, titanium is hard enough to resist many forms of wear and tear. Despite its toughness, titanium can be ductile, meaning it can be bent, formed, or drawn into a wire, especially when it's very pure and handled in the right conditions. However, one quirk: titanium's ductility can be reduced if it has oxygen or other impurities in it. High purity titanium in an oxygen-free environment is quite ductile and easy to work. But titanium also has a strong appetite for oxygen. Even a little oxygen picked up in the metal can make it less flexible and more brittle. So, working with titanium, casting, forging, etc., often requires very careful control of the atmosphere and impurities. Titanium has a high melting point of about 1668 degrees Celsius or 3034 degrees Fahrenheit. That is much higher than aluminum with 660 degrees Celsius, and a bit higher than steel. Steel's melting point varies roughly around 1500 degrees Celsius depending on the alloy. Because of this, titanium can withstand moderately high temperatures without losing its strength. An important trait for things like jet engines or a spacecraft that get hot. Now, as we could see earlier, titanium is lustrous and silvery white in appearance. Polished titanium looks similar to stainless steel, but maybe a shade darker or more gray. It's also famously non-magnetic. Technically, it's paramagnetic, meaning any magnetic effects are extremely weak. You can't pick up a titanium object with a magnet, a fact that surprises some people who assume that all metals are magnetic. Well, they're not. Additionally, titanium is a relatively poor conductor of heat and electricity compared to metals like copper or iron. Beyond its mechanical strength, titanium has some chemical superpowers. Chief among them, it doesn't rust or corrode easily. If you've ever heard that titanium seems almost impervious to the elements, that's because of its special relationship with oxygen. Now, titanium has a natural ability to passivate, which means it spontaneously forms a very thin oxide layer on its surface when exposed to air. The moment fresh titanium metal is in contact with oxygen from water or air, it oxidizes to form titanium dioxide on the surface. But unlike iron oxide, which is flaky and allows corrosion to continue, titanium oxide clings tightly and seals off the metal underneath from further reaction. This oxide layer is extremely thin, initially only a few nanometers, just a billionth of a meter thick, invisible to the eye. Yet it is enough to protect titanium from things that would eat away at other metals. Over time, this protective layer can slowly grow a bit thicker, a few more nanometers over the years, making the protection even better. The result? Corrosion resistance. Titanium can withstand rain, seawater, and even chlorine. It doesn't mind a salty ocean environment at all. Unlike steel that would rust rapidly, it's resistant to most acids in moderate concentrations and temperatures. Now, for example, dilute sulfuric acid or hydrochloric acid, common strong acids, won't do much to titanium at room temperature. This is why titanium is a preferred material for chemical processing equipment that handles corrosive substances. Even bleach, sodium hypochlorite, or chlorine gas, which are very corrosive to most metals, can be stored or processed in titanium vessels. In fact, titanium is one of the few materials that can hold up in bleach manufacturing environments. However, titanium isn't chemically invincible to everything. There are certain substances that can penetrate or destroy that oxide layer. Hydrofluoric acid is one of those acids. This particular acid is the kryptonite of titanium and glass too, incidentally. Dilute hydrofluoric acid will attack titanium's oxide layer and dissolve it, allowing it to then react with the underlying metal. So titanium equipment cannot be used with hydrofluoric acid. Now, another example is hot concentrated acids. While titanium laughs at many acids when they're cool or dilute, hot concentrated strong acids like hydrochloric or sulfuric acid will corrode it. Heat and concentration tend to eventually eat through that protective oxide. Extremely alkaline or basic solutions at high temperatures can also attack titanium to some extent, though it's generally more resistant to alkali than to strong acid. Now, at room temperature, titanium is quite content and inert due to its oxide shield. But when you heat things up, titanium shows its more reactive side. In fact, titanium is a very reactive metal. We just normally don't see that because of the passivation effect. Now, if titanium is heated in the presence of air, at some point it will start to burn. Yes, you heard that right, this metal will start to burn. Titanium can catch fire in air at elevated temperatures, well below its melting point. This is one reason why welding or machining titanium requires special caution. Fine titanium shavings or powder can ignite like flash powder if you're not careful. When titanium burns, it reacts with oxygen, forming titanium dioxide, or with nitrogen, forming titanium nitride. Fun fact, titanium is one of the few elements that can burn in pure nitrogen gas. Normally we think of nitrogen as quite inert. For example, steel doesn't burn in nitrogen, but titanium at around 800 degrees Celsius can grab nitrogen out of the air and form a hard, brittle, ceramic-like compound. Yes, ceramic. I do read almost all the comments of this channel, and we do try to do better every time. And it will form titanium nitride. Now this is why when working with titanium at high temperatures, an inert atmosphere like argon gas or vacuum is needed. Otherwise, the metal will react with the air and ruin its quality. Now similarly, at around 1200 degrees Celsius in air, titanium will rapidly oxidize, and at 610 degrees Celsius in pure oxygen, it will ignite into titanium dioxide. It's also very reactive with halogens, like chlorine, fluorine, etc. At high temperatures, for instance, titanium will combine directly with hot chlorine gas around 550 degrees Celsius to form titanium chloride. Now, because titanium wants oxygen and other non-metals so badly at high temperatures, we melt or cast titanium in vacuum or inert gas only. If you try to melt titanium in an open-air furnace, you'd end up with a fire and a mess of brittle compounds, not useful metal. Now, chemically, another important aspect is that titanium is non-toxic and biocompatible. It doesn't react with our body's chemistry. Titanium is not poisonous. In fact, you probably eat and inhale micro amounts daily with no harm. And titanium dioxide is commonly used as a white food coloring or in toothpaste. Now, as a result, you can have a piece of titanium inside you, like a hip implant or a dental implant, for decades with no ill effects. The body basically ignores it. So let's talk a little bit about the paradox from the title and the reason you probably clicked on this video. In addition to pure metal and regular alloys, titanium forms some interesting intermetallic compounds that are noteworthy. An intermetallic is basically a specific compound of two or more metals, or a metal and a metalloid that has its own crystal structure and often very different properties from the parent metals. Now, titanium's intermetallic compounds have opened up new frontiers in material science, offering specialized performance for demanding applications. Let's look at a couple of important examples in simple terms. When titanium and aluminum are combined in certain fixed ratios, they form intermetallic compounds such as titanium aluminide and alpha-2 titanium aluminide. These are not just random mixtures, but ordered compounds. So, what is so special about them? Well, they are extremely lightweight, even lighter than typical titanium alloys, and can withstand high temperatures better than normal titanium metal. For example, titanium aluminide has a density of around 4 grams per cc. Pure titanium is about 4.5 grams per cc, and nickel superalloys are 8.5 grams per cc. Titanium aluminide also remains strong at temperatures of 600 to 800 plus degrees Celsius, has a good oxidation and creep resistance at those temperatures. This makes it a candidate to replace much heavier nickel-based superalloys in some parts of jet engines or gas turbines. Imagine a jet engine's turbine blades, traditionally made of nickel alloy, heavy, but they survive the heat. If you could make them out of titanium aluminide, they'd both be half the weight, which could improve the engine's thrust-to-weight ratio and efficiency. Now, indeed, since the 2000s, some manufacturers have started using titanium aluminide for low-pressure turbine blades in aircraft engines. These blades operate at the back of the engine where it's cooler than in the front, but still very hot for normal metals, a perfect spot for titanium aluminide. The reduction in weight helps the engine's performance. The catch? These intermetallics are often brittle, especially at lower temperatures. That means they don't bend or deform easily. They tend to crack if overstressed or shock-loaded. This brittleness made them hard to work with and limited their use for many years. Now, material scientists have been tweaking alloying additions and processing methods to improve ductility. Progress have been made, and now titanium aluminides are on the verge of more widespread use in aerospace. They truly are a unique class of material, kind of a bridge between metals and ceramics. Yes, I said it right again. Like aluminum, strong like superalloy, but brittle like a ceramic. In short, titanium aluminides are enabling lighter and more fuel-efficient engines without sacrificing high-temperature capability. Now, what I have here is another famous titanium intermetallic, or alloy. It's nickel titanium, commonly known as Nitinol. This is roughly an equal mixture of nickel and titanium, about 50-50 atomic percent. Nitinol doesn't form a simple mixture, it forms an ordered phase that gives it remarkable properties, shape memory, and super elasticity. Now, this almost seems like magic. Shape memory effect means that you can deform an object made of nitinol, bend and twist it, and as long as it is below a certain temperature, it stays that way. But heat it up above its transformation temperature, and it will spring back to its original shape, as if by magic. Super elasticity means that at warmer temperatures you can bend it a lot and it will snap back immediately upon release, like an extremely rubbery metal, as long as you don't exceed a certain strain. And this is what we show here. I have this paperclip made of nitinol. As you can see, I shaped it differently, and now that I heat it, it will just spring back in its paperclip state. These properties come from a solid-state phase transformation between two different crystal structures. A low-temperature phase called martensite and a high-temperature phase called austenite. Similar terms are used in steel, but different mechanism. What's amazing is that nitinol can undergo much more deformation than normal metal without permanent damage, on the order of 10 to 30 times more elastic strain than, say, spring steel. You're probably wondering, what can we use this for? Because it's such a magical metal. Well, lots of really cool things. Nitinol's biocompatibility and super elastic nature make it perfect for devices like stents. Tiny mesh tubes that surgeons insert in arteries, cold and collapsed, then body warmers make them expand to prop the artery open. Or for guide wires and surgical tools that need flexibility. Dental braces wires have used nitinol so they can apply constant gentle pressure as they try to spring back to the original shape. Memory metal glasses can be bent and will return to shape. Often use nitinol alloy for the bridge or temples, so you can sit on your glasses by accident and they won't snap. They'll bounce back, mostly. Now, nitinol was an accidental discovery in the 1960s during research from missile nose cones, and it's a great example of how combining titanium with another metal, nickel, in the right way yields an entirely new property that neither metal alone had. Titanium can form intermetallic compounds with other elements too. Some are troublesome, like iron. If you weld titanium to steel improperly, you can form brittle titanium iron. Intermetallics that cause cracks. Others are currently being researched, like titanium silicides or titanium with certain rare earths for special electrical applications. But in terms of broad significance, the big two are covered: titanium aluminides and nitinol. These materials still carry some of titanium's indestructible spirit. For instance, a titanium aluminide turbine blade can survive punishing heat that pure titanium could not. And a nitinol stand can flex repeatedly without breaking where normal metal might fatigue. They are specialized, yes, but they expand the realm of what titanium can do and continue to be a hot area of material science research. So, when weakening titanium by letting it alloy up will actually make it, in the case of titanium aluminide, almost indestructible. Now, titanium might seem like a high-tech space-age metal, but it's actually plentiful on Earth. In fact, titanium is the 9th most abundant element in the Earth's crust, making up about 0.6% of the Earth's crust by weight. That's more common than many better-known metals. For example, there is more titanium than copper, and it's the 7th most abundant metal overall. However, you're not going to pick up a chunk of pure metallic titanium on the ground. It's never found in its pure form, naturally. Titanium is always bound to other elements, usually oxygen. In nature, titanium is typically found in mineral forms. The most significant titanium-bearing minerals are rutile, ilmenite, anatase and brucite, titanite, and perovskite. Australia, South Africa, Canada, India, Mozambique, Norway, Ukraine, and China are examples of places with large deposits of titanium-rich sands or rock deposits. Often, these are mined by a process of dredging or surface mining, and then separating the heavy minerals. Even though titanium is common, rich concentrations of its ore are less common. It's kind of everywhere but in small amounts, in many rocks. So we target the few spots where geologic processes have gathered a lot of ilmenite or rutile together. Getting titanium from its ore is not easy. It's one of the more complex metal extraction processes. Why? Because as we learned, titanium just loves oxygen. Its ore are oxides like titanium dioxide or iron titanium trioxide, and it holds that oxygen tightly. We can't simply throw it in a hot furnace with carbon the way we do with iron ore or a blast furnace, because titanium would rather bond with the carbon than let go of the oxygen, yielding titanium carbide, which would be brittle and useless. So we had to develop a multi-step process to extract the metal. Now, I'm not going to walk through that process in this episode. If you want me to do so, let me know in the comments and I can make a special episode just about that, focusing on the Kroll process. Now, it's worth noting that the Kroll process, invented in the 1940s, is still the dominant method for producing titanium metal. It's batch-based, energy-intensive, and expensive. That is one big reason why titanium is pricier than common metals like steel or aluminum. Researchers have long sought cheaper methods. One alternative, the older Hunter process, used sodium metal instead of magnesium to reduce titanium tetrachloride. It works similarly, but it's costlier and mainly of historical importance now. Another method, the iodide process, also known as the Van Arkel de Boer process, was used in the 1920s to make ultra-pure titanium. It involves forming titanium tetraiodide gas and decomposing it on a hot filament to pure titanium. It yields super clean titanium, but it's too slow and small scale for bulk production. Think lab quantities. Modern innovations include processes like the FFC Cambridge process, which attempts to reduce titanium oxide directly to metal via electrolysis in a molten salt. There's also ongoing work on continuous processes or using hydrogen in clever ways. But as of now, if a product is made of titanium, those metal grains in it are likely coming from the Kroll process. The production ends up generating a porous sponge, then ingots, and then all the shapes that we use. Now, we already talked about this, but if there's one industry that loves titanium, it's the aerospace industry. Approximately 2/3 of all titanium metal produced goes into aircraft engines and frames. The reason is simple. In aircraft, every kilogram saved in weight improves performance and fuel efficiency, but you can't sacrifice strength or safety. For example, titanium alloys are used extensively in jet engines for compressor blades, rotors, and other parts that face both high force and elevated temperatures, as well as in airframes like critical structural beams, leading gear, and firewall panels that must resist heat and corrosion. A commonly used alloy is Ti6Al4V, titanium with 6% aluminum, 4% vanadium, which hits a sweet spot of strength, weight, and workability. About half of all titanium in an aircraft is this alloy. Historically, aircraft like the Lockheed SR-71 Blackbird were groundbreaking in their use of titanium. Over 90% of the SR-71 structure was titanium. This enabled it to fly at Mach 3, 3 times the speed of sound, without melting, as well as stay relatively lightweight. Now, titanium has literally been a lifesaver, or at least a life enhancer, for countless of patients, because it is biocompatible and it doesn't rust inside the body. But we've already discussed this in earlier chapters. Titanium brings an edge to sports equipment for those who seek top performance. It started showing up at high-end golf clubs where a titanium driver head allowed a larger club size without excessive weight, helping golfers hit harder and further. In tennis, some rackets have titanium reinforcement or frames, making them lighter and stronger than traditional designs. Bicycle frames made of titanium are prized among cyclists. They're lighter than steel frames, but offer a famously smooth ride. Now, titanium isn't used in construction as widely as steel or aluminum due to cost, but when it is used, it makes a statement. One of the most famous examples is the Guggenheim Museum in Bilbao, Spain, which is sheathed in gleaming titanium panels on the exterior. The architects chose titanium not only for the look, it has a lovely subtle glow and color that changes with the light, but also because its longevity. Those panels won't corrode in the rainy atmosphere of Bilbao. Now, since then, a few other buildings have sported titanium cladding or roofs, like the Cerritos Millennium Library in the USA and some monuments in Russia. The monument of Yuri Gagarin, for instance, is made of titanium. Now, we're going to skip a couple of applications, but finally one of the biggest uses of titanium isn't as a metal at all, but as a chemical compound. Titanium dioxide is the ubiquitous white pigment used in paints, paper and plastics. About 95% of titanium mined goes into making titanium dioxide pigment. It gives that bright, opaque white in everything from house paint to the white lines on the road to the frosting-like filling in Oreo cookies. Yes, titanium dioxide is used in some foods and toothpaste for whiteness. Next time you see a sleek airplane, a shining piece of modern architecture, or even brush your teeth with gleaming white toothpaste, think of titanium, the metal that went from realm of the Titans to everyday life. Now, if you think I missed anything, leave it in the comments, and if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, if you would like to know more about aluminum, watch this episode next.